Today we'll continue the class. Last Bode plot. Let me share the whiteboard. I hope you can see the whiteboard. In the last class, we stopped at plotting the Bode plot for 7th basic factor, that is 1 by 1 plus j omega t. So for that we calculated error, that is 3 dB at corner frequency, 1 dB at half the frequency. So this is your last class notes. So at omega equal to 1 by t, it's called break frequency. So we found the error at half the corner frequency. So similarly, we find the error for higher frequencies. Okay. So let us see the error function. So for one by t less than or equal to omega less than infinity. So what's the error magnitude? The error magnitude is, what's the error magnitude? It is the original value minus approximated value. So what's the original value? It is minus 10 log 1 plus omega square t square. This is your original value minus, what's the approximate value for this period? It is minus 20 log omega t, right? So calculate the error at corner frequency for this range. So we are calculating the error for 1 by t less than or equal to omega less than infinity. So first let us find out the error at the corner frequency. The error, yeah, do you have any problem? You got some warning. Okay. So the error at corner frequency, that is at omega equal to t, 1 by t. At omega equal to 1 by t. It's a corner frequency. So for this range, what's the value? So it will be minus 10 log 1 plus omega square is 1 by t square gets cancelled. Again, we'll get 1 here. Now minus gets cancelled. It will be plus 20 log 1. So what's the value? So again, the value will be minus 3.03 dB, or approximately. Or approximately, I can say it is minus 3 dB. So identify the difference when we are taking the frequency range from 0 to 1 by t, that is corner frequency. At the corner frequency, we got the same value, minus 3 dB. And half of the frequency, half of the corner frequency, the error is minus 1 by t. You must remember these values for correcting the Bode plot. Now, let us look at the another point that is set at double the corner frequency. So the error, this is that corner frequency, I can say corner frequency. You want to find out the error at twice the corner frequency. That is omega equal to Q by T. So at omega equal to T by T, what's the value? Again, we'll substitute the value. It is minus 10 log 1 plus omega square T square. So what is the value? It will be 4 here, right? Plus 20 log 2. So if you calculate this value, again you will get minus 0.97 or 98 dB. I can say it is minus 1 dB approximately. Okay. So this is how you can find the errors in the basic factor of type 1 by 1 plus j omega t. So what does it mean? Whenever you have this type of basic factor, you will get two asymptotes or two straight lines which are meeting at the corner frequency at omega equal to 1 by t has some correction factor. So what is the correction factor? First we will draw the approximate graph for the basic factor 1 by 1 plus j omega t. One is below the corner frequency, it is 0 dB line. So no need to add that slope for previous basic factors. And then another one is after t, after the corner frequency, it is minus 20 dB per decade. Now, where do you make corrections? It is at corner frequency. It should be, suppose if the value is minus 6 dB, you must make it as less than that, minus 3 dB. That is minus 90. So similarly, at the half the frequency or double the frequency, the correction is minus 1. So that's about the basic factor 1 by 1 plus j omega t magnitude plot. So let us look at the phase angle. The phase angle. The phase angle pi of the factor 1 by 1 plus j omega t. So the phase angle here says pi is equal to minus tan inverse omega t. So how do you find the phase angle? Let us take few values and find out the phase for those values at omega equal to 1 by t. So what's the phase angle? And at omega equal to 1 by 2t, what's the phase angle? That is pi here, I'll write it here. And again, at omega equal to 0, what's the phase angle? At omega equal to 1 by 10t, that is we are going down, what's the phase angle? Right. And at omega equal to infinity, obviously it is minus 90 degrees, and at 2 by t it is minus 63.4 degrees. Let us write it here. At omega equal to infinity, it would be value will minus 90 degrees, and at omega equal to 2 by t, that is double the frequency, and it will be minus 63.4 degrees. So if you calculate other values, it will be minus 45 degrees, minus 26.6 degrees, and then it will be 0 degrees, and for 10th it is minus 5.5 degrees. So this is how you can have the phase angle values of 1 by 1 plus j omega t. So let us draw the Bode plot for all these values. So let us draw the Bode plot for this 1 by 1 plus j omega t. So it would be take 2 axis log omega. Should draw it here itself. So I'll take one more axis log omega. So let us move up so that we can draw the graph. Okay, and this would be your magnitude plot in dB. In dB, magnitude plot, and this would be something like 0. Let me say it is minus 20 dB. Since it is minus 20 dB per decade, so let me take it as minus 20 dB, and then here I'll take 0 degrees. Here itself it's a pi. So then it would be minus 45, since we got some minus 45 degrees and minus 90 degrees. So something like this, right? So let me put here the first magnitude plot at omega equal to 1 by t. So let me denote it as omega c. So it is omega c. Assume this is your corner frequency. Omega c is equal to 1 by t. It's a value. And then we have 10 times of your value, that is 10 by t, right? So we'll get, I'll draw some dotted lines here. Very important, later we'll see it. Then at corner frequency before 1 by t, it is 0 dB line. So I'll draw it with another color. So it is blue color before corner frequency. I'm making it as thick. And then after the corner frequency, it is minus 20 dB per decade. And we know that whenever it is minus 20 dB per decade, it would be like this, right? So I have some value here. This point is at doubly or 10 times of the corner frequency, isn't it? Minus 20 dB per decade means for every decade, the magnitude is decreased by minus 20 dB. So that's why we have one point here. So if you further take the values, that is omega c equal to, and double the value 100 t, it will be minus 40 dB. Then it will be 1000. It keeps on going as a step. So this is the approximate clock. You remember one point here. This is what we call it as approximate plot. Since we made some approximations, right? Approximate plot. Okay. So then let us look at the exact plot. What's the exact plot? If you make some corrections, we will get the exact plot. So let me take a color for this. So what is the correction factor at omega c? It is minus 3 dB, right? So it would be something like this here, minus 3 dB. At half of the frequency, you have 1 dB, right? Minus 1 dB. I'm putting here. And double the frequency, that is when omega c equal to 2 by t, it would be something like here, I can say, okay, these are the points, right? So to draw the exact plot, you should draw the smooth curve joining all these points. That's enough. So no need to find out all the values since we don't have enough time for drawing all these things. So that's why we found only the correction factors at corner frequency and also half the corner frequency and double the corner frequency. So let me draw the exact plot. So it will be start at 0 dB. Yeah, it's going like this, joining all these points. Let me. Okay, anyway, I assume this is a smooth curve, joining these points here, right? Maybe something like this, right? So the value will be, so this arch, you draw all these points here like this, right? So what is this? This is your exact plot. I can say this blue color is your exact plot, right? So this is about exact plot, magnitude plot, approximate plot, and exact plot. So let us again look at the phase plot. So at corner frequency, what's the value? At corner frequency, I hope it is minus 45 degrees. Let me check. Yeah. So at corner frequency, it is minus 45 degrees, and omega tends to infinity, it is minus 90 degrees. So obviously, and at omega equal to 0, I can say at omega equal to, yeah, then it would be, the point is, when I say, that's why I draw this dotted line at omega equal to 0 is, oh, this would be something like this. If you take full more values, it would be like this. So it will touch. Okay. So approximately it will be like this. You draw it smooth curve again, right? So this is your phase plot, right? Phase plot, right? So this is about the basic factor 1 by 1 plus geometry. So if you understand this plot, this particular factor, it's very easy to draw the Bode plot. So let us look at the next basic factor quickly. The next basic factor is the same, but with n. Next basic factor is 1 by 1 plus j omega t whole to the power of n, right? So this is about, so obviously you'll get the magnitude of this basic factor is 20 log magnitude of 1 by 1 plus j omega t whole to the power of n. This would be minus 10n log 1 plus omega square t square. So obviously we have some corner frequencies and approximation for this for low frequencies. It would be 1 by 1 plus j omega t whole to the power of n. This would be minus 10n log 1 plus omega square t square. Even for omega greater than 1 by t, it would be, the magnitude would be magnitude of 1 by 1 plus j omega t whole to the power of n is minus 20n log omega t. So you made some simple mathematics, you'll get this. So the magnitude plot can be approximated by two straight lines. One is 0 dB and other one is minus 20 dB per decade. Only thing is n, and we saw it before many basic factors. So that's about eighth factor. So the corner frequency will get the same graph, but multiplication by n. So that's why I am skipping this. You try this. Just add n in the magnitude part. You revise all your basic factor. So the corner frequency would be omega c. Omega c is equal to 1 by t. We know that. And the error at the corner frequency is what is that? Is minus 3n into dv. So what's the error? You just multiply with your n here at corner frequency. What's the phase angle? Phase angle would be minus 1 nd. I can say dv at c at omega c, and this would be at error at double the frequency of the frequency, that is 2 by t and 1 by 2t, right? So what's a phase angle? Phase angle would be minus 45 degrees into n. So instead of putting minus 45 degrees, you just multiply with n. So that's about basic factor 1 by 1 plus j omega t whole to the power of n. So let us move on to the next basic factor. You try this one. Just multiply, draw the Bode plot and magnitude plot. Sorry, phase plot and magnitude plot. Next one, ninth factor, that is 1 plus j omega t, right? So again, it would be same. See, once you do, it's very easy. Then it would be minus 20 log magnitude of 1 by 1 plus j omega t, isn't it? We can write it this way. So even for phase angle, it will be 1 plus j omega t. So would be tan inverse omega t. So you'll get the positive values, right? Or you can say minus phase angle of 1 by 1 plus j omega t, right? So quickly note down this. So what's the advantage in the board diagrams? If you have some factors, reciprocal factors, the log magnitude and phase angle curves need only change in the sign. So therefore, magnitude plot can be approximated by, again, the two straight line. So one is 0 dB before low frequencies, and other frequency that is plus 20 dB, right? So what's the magnitude plot for this? So you also draw for this. I'm giving for low frequencies. It will be 0 dB line, and higher frequencies, I write it here. For higher frequencies, it will be plus 20 dB per decade. So that is 1 by t. Obviously, phase angle would be plus 45 degrees. That is pi is equal to, I think we, okay. So plus 45 degrees at corner frequency, right, at omega c. And this is higher frequency means the value is 1 by t less than omega less than infinity. Lower frequencies means 0 less than omega less than 1 by t. Right. So this is about the zero basic factor. So similarly, we can also draw the Bode plot for 10th basic factor. So which is 1 plus j omega t whole to the power of n. So you can quickly write the equations for this. So it would be 20 log 1 plus j omega t whole to the power of n. So or I can say 10n log 1 plus omega square t square. So again for omega less than 1 by t, it would be magnitude would be 1 plus j omega t whole to the power of n would be 0 dB line, and for omega greater than 1 by t, the magnitude would be j omega t whole to the power of n. Magnitude would be 20 n log omega t. Right. So one is 0 dB for so I can say one is 0 dB line for 0 less than omega less than 1 by t, and the other one or second one that is at higher frequency is it will be plus 20 n into dB for decade. So the error would be the same. It's like error would be plus 3n into dB. So it would be plus minus, and the phase angle would be 45 degrees into n, right? So we'll get the reverse curve. One is plus 20 dB for 0. For pole, it is minus 20. You just remember this point. It's very easy to draw the Bode plots. Or you can even remember all these Bode plots by comparing all the values. So this is 10th basic factor. Now we can have one more basic factor. Malan, I can quickly write the equations and we'll finish this topic today. So 11th one, it is 1 by, it's a long equation, but we need only the Bode plot for this. So I'm not going to do all the derivations here. Just remember the value. It is quadratic factor, that is quadratic pole. This would be 20 log magnitude of 1 by 1 plus 2 eta into j omega by omega n plus j omega by omega n whole square, right? And this would be minus 20 log root over 1 minus omega square by omega n square whole square plus 2 zeta into omega by omega n whole square, right? So again, for low frequencies, that is omega less than much less than omega n, the log magnitude becomes minus 20 log 1. So that would be 0 dB. The log magnitude becomes minus 20 log 1. So that is 0 dB. For higher frequencies, so for high frequencies, sorry, for high frequencies, it would be, that is omega greater than omega n, the log magnitude is minus 20 log omega square by omega n square. So this would be minus 40 log omega by omega n dB, right? So for higher frequencies, the asymptote is a straight line having a slope of minus 40 dB per decade. So for quadratic pole, the value, the magnitude value would be doubled. So that is minus 40 dB per decade. You must remember this value. The slope would be 40 dB per decade. So it's a phase angle. So I'll write it here, phase angle. The phase angle pi is equal to minus tan inverse 2 zeta into omega by omega n by 1 minus omega by omega n whole square. So for 12th one, what will happen? It would be for 12th basic factor, that is 0, quadratic 0. 12th basic factor, quadratic 0, it will be plus 40 dB per decade, and the phase angle would be, you get the plus value. Phase angle is plus tan inverse, the same value, write it here. Right. So these are the basic factors used in Bode plot. If you have any questions, you can ask till this point. So if there are no questions, let us move on to the next step. So all of you studying general procedure for constructing Bode plots. Next step in this Bode plot. So let us summarize all the points for constructing Bode plot. So put the heading. You can write it as general procedure for constructing Bode plot. So you must note down all the points since we follow these steps for constructing Bode plot. So what is the transfer function for g of j omega into h of j omega? So for this, we are plotting the Bode plot. So what's the first step? Step number 1. Rewrite the sinusoidal transfer function as a product of basic factors in time constant form. So that's the first point. Rewrite the sinusoidal transfer function as a product of basic factors in time constant form, right? So let me write it here. Rewrite the sinusoidal transfer function as a product of basic factors. Very important point, basic factors. So in time constant form. So what's the key point here? We should write in sinusoidal transfer function. Then it should be written in the in terms of product of basic factors, right? So if you don't write your transfer function in terms of basic factors, you cannot draw the Bode plot. And also, what's the form? It should be time constant form. So these are the key points in the first step. Second step. Identify the corner frequencies associated with each one of these basic factors. Very simple step. Identify the corner frequencies associated with each one of these basic factors. So after writing the basic factors, you identify the corner frequencies. So as a find, identify corner frequencies. Third step. So knowing the corner frequencies, draw the asymptotic magnitude plot This plot consists of straight line segments with line slope changing at each corner frequency by plus 20 dB per decade for a 0 and minus 20 dB per decade for pole, and also plus or minus 20 m into dB per decade for 0 or pole of multiplicity m. For complex conjugate 0 or pole, the slope changes by plus or minus 40 dB per decade. So here is the summary of the third point. I'll write it here. Knowing the corner frequencies, so we should draw the asymptotic magnitude plot. First thing is I should draw asymptotic magnitude plot, right? So what is this asymptotic magnitude plot? It has straight line segments with line slope changing, right? So it is having straight line. What is this? These are straight line segments. What are these? It's a straight line segments with line slope, that is asymptotic line slope, changing at each corner frequency. What is that? Line slope will change at each corner frequency. So how they change? Let me write summarize all the basic factors here. Plus 20 dB per decade. What is this? Plus 20 dB per decade minus 20 dB per decade. So where do you get this? So this is for pole at the origin, right? And this is for 0. Recall the I'll simply write pole and 0 so that it's very easy to remember. And then plus 20, right, plus or minus 20 m dB per decade. What is this for? Pole slash 0, right? So with multiplicity factor m. I just change it to m. And then for complex conjugate 0 or pole, that is last one, it would be plus or minus 40 dB per decade for pole or 0. You identify the similarities and differences in these slopes. See, for all poles, sorry, we did some wrong thing here. This is for pole, this is for, see, for all poles it is a negative value. For all zeros, it is positive value. And also your magnitude will be doubled for the quadratic poles. It is minus 40 dB. If you have a multiplicity factor, just multiply with them. So this is how you must remember all these values for all the basic factors. So once you remember all these magnitude, plot, slopes, you can easily draw the construct the Bode plot. This is the third point, very important point. Fourth point, determine the corrections to be applied to the asymptotic plot. So what is this plot? We should draw the approximate plot first, then we should do the correction. So find out or determine the corrections. So when do you get corrections? If you have the pole of the type 1 by 1 plus j omega t, or 0 of type 1 plus j omega t, or whole to the power of n. And also for quadratic poles, the correction factor would be, have I mentioned here, will be multiplied by n. I wrote slope here. Yeah. So error is, see this, it is multiplied by n. It is, if it is n equal to 2, it would be 6. So what about this? This is minus 6 dB. Here we'll get minus 6 dB correction at corner frequency, and also minus 3 dB at the of the points, quadratic poles, right? So these are the correction vectors for the quadratic poles. So determine the corrections to be applied. Right, to the asymptotic. Right. Fifth step, draw smooth curve through the corrected points such that its asymptotic line segments. This gives the actual magnitude plot. So draw the smooth curve. Draw the smooth curve. Curve connecting all these corrected points, right? And make corrected points. Right. So the final steps, till this point we discussed only the magnitude plot. The final step would be phase angle. That is, calculate the total phase angle of g of j omega into h of j omega at different frequencies. And plot the resultant phase plot. So these are the 6 steps for drawing the Bode plot. So we quickly revise or steps procedure. The first step is we should write the your transfer function in terms of sinusoidal transfer function and product of basic vectors, and also as well as in time constant form. And identify the corner frequencies or draw the approximate graph by keeping all these basic factors in mind. Then fourth one is apply the corrections needed and draw the smooth curve for the corrected points. Finally, calculate the phase angle and draw the resultant phase plot. Right. So let us take one simple example for drawing the Bode plot. So the first example in Bode plot. So example number 1. So that is G of S into H of S is equal to 54 into S plus 4 by S into S plus 1 into S square plus 1.8 S plus 36. Right? So this is your transfer function. Should construct Bode plot for this. So draw the Bode plot. So if you have a logarithmic sheet, you try to draw this plot on the logarithmic graph. So after completing this example, so let us first apply the step 1. So what is step 1? We should find out the sinusoidal transfer function and also write in the form of basic factors, product of basic factors, right? So let us do that. So convert, and also we should write it in the time constant form. Step 1, light summary here. First, it should be we should find out sinusoidal transfer function, and then time constant form, and then basic factors. Basic factors, right? So let us start with the time constant form, so that it's very easy to convert into sinusoidal transfer function and also basic factors, right? Let us write them as G of S into H of S is equal to. So what's the time constant form? I should write it 1 plus S, 1 plus S, something like this. So just multiply with 54 into 4 in the numerator. So it would be 1 plus S by 4 here by. So here in the denominator it is S into 1 plus S only. So I need to touch this. The next one is quadratic pole. We should write it as 1 plus 1.8 S by 36 plus S square by 36, isn't it? So you have 36 here. Just divide all these terms. So if you are dividing, you should multiply with 36. Here I am writing 36. Okay. So let us recalculate this value. G of S into H of S would be 6 into 1 plus s by 4 by s into 1 plus s into 1 plus 0.3 into s by 6 plus s by 6 whole square, right? So this is the time constant form. And also we wrote in the basic factors. Right? So let us stop it here. You just replace s equal to g omega. You will get the sinusoidal transfer function. We finish this first step and we'll continue this class later. Let us write a sinusoidal transfer function g of j omega into h of j omega. It would be 6 into 1 plus j omega by 4 here by j omega into 1 plus j omega into 1 plus 0.3 into j omega by 6 and also j omega 6 whole square, right? So step 1 completed. So we'll see step 2 and 3 in the next class. So if you have any doubts, you can ask. So if you don't have any doubts, you can leave the meeting. If there are no questions, let us leave the meeting.